straightforward. Good. So this week we won't have lecture Wednesday because I'm traveling. So we will have lecture now, and we will have a makeup tomorrow 5 p.m. Okay, not today 5 p.m. There's a colloquium stuff, so if possible, I'm trying to avoid conflict. So tomorrow 5 p.m. Who cannot join that? Okay, so mostly it works for you. Mostly. So today we will have lecture now, and then we will meet again tomorrow 5. Okay, for the makeup, and then I will announce another makeup next week once we meet. Okay, let's jump in. If we have a talk. Okay, so what we talked about was we started our discussion on Green's function. So here's a quick reminder. So I define an object. So this thing as a sum over all Feynman diagrams, right? So sum over all Feynman diagrams. So this thing is sum over all Feynman diagrams. Now, including, not exactly the same order as I wrote, including propagators for external legs. And also, we allow that external legs are not necessarily on shell, so it can be off shell. And then we said that that thing should include both the connected as well as disconnected diagrams. Okay, so that's sort of an operational definition of this thing. And eventually, what we have seen, and then one important thing is that we sort of discussed quickly that we can extract the S matrix out of that object. So far, this discussion inspired by our tree-level discussion, okay? And then we say, okay, we can actually extract the S matrix from that, whatever function we define, by amputating the external propagators and then setting it to be on shell. So that's how we saw it works that way. But again, this is not a construction possibly working for arbitrary QFT, which is non-perturbatively defined. Okay, so that's what we will do. For now, this is based on our tree-level intuition. And then we define this object, Gaussian space object, by taking a Fourier transform of that. So let me not even bother to write down that long expression. So starting from this, we can do the Fourier transform to get that object. Now, I'll talk about two things. First, we were able to talk about this object coming from one object, which is basically, when we do that, we define our Hamiltonian or Hamiltonian density, including this one, what we discussed, the source term, right? There's a source, this is the source. Then we saw that this can be seen in momentum space by having this structure. Or if you like, you can also get the expression in the space. But I just wanted to say one thing about this thing, which I'm not sure if I said that. So from this, you see that this is basically a coefficient of this object, which physically, I draw a picture, nothing but vacuum to vacuum transition amplitude in the presence of source, right? So if you recall, I draw this picture, so the introduction of a source will all of a sudden allow us to talk about, so this is the time, so long time ago it was a vacuum, and then long time later it's vacuum again, but thanks to this source, we can still talk about sort of a scattering process looking diagram, because now source can either produce particle or it can detect the particle, right? And now I can do as if I can do the perturbation theory in powers of this source, and the coefficient is nothing but that momentum space Green's function, which is included all diagram to all orders in perturbation theory of the original couple that we are interested in, right? Versus U couple. So that's what we talked about. So in that sense, this object is called a generating function. Of one kind, but anyway, so it is called the generating function of all diagrams, not only connected but also disconnected diagrams. And then what we saw was that that same object can be expressed, so far still summarizing it, now in the original space picture. And then we have this. So this picture then allowed us to interpret this thing as nothing but a Green's function, right? Meaning it encodes not only linear but also non-linear, infinite number of response of the system to an external perturbation, right? So you have a quantum field theory system, you do something by external probe, and then this is how the system reacted. So that's the infinite set of non-linear response. Okay, hence Green's function. So from this expression, it should be clear that you can now obtain Green's function. Endpoint function is a functional derivative of this generating function, hence it is named by taking functional derivative. Okay, so that's sort of what we talked about until last time. Probably other than the fact that I did not write down this explicitly, and probably I did not point the name explicitly. So I just wanted to do that before we start. Okay. So far, this is just a summary. Now we will do our main discussion. So our main discussion start out with the question. Okay. The first question is, can we define an analog of this generating functional valid to all orders in perturbation? Okay, so I'm writing this question to make the difference sharp. So again, we developed this machinery based on tree-level intuition. Okay, now I'm asking, is there an analog that is valid arbitrary Q interacting QFT? Okay, so not necessarily relying on perturbation theory. And if so, if such object exists, next question is how to extract S matrix out of that. Okay? Again, sort of non-perturbative. Okay? So that's the question. We are going to answer the rest of the lecture. So today, hopefully, I will finish up the discussion and derivation of the first part. And then the second part is the question of LSZ reduction, which probably we will have to wait until next week. Okay, so that's or tomorrow. So that's the game plan. So I will define an object which is valid regardless of the strength of the interaction in your QFT. So we will define that, and then establish the fact that whatever the object I'm about to define do have an interpretation in terms of a sum of all Feynman diagrams. Okay, so that's the goal. Let's go.
Professor?
Yes.
Sorry, because I was at rest. So how did you define the generic function then?
Which I just wrote down. So this is given a momentum space Green's function, okay, which is defined as the sum of all Feynman diagrams, including external lengths and momentum conserving delta function. Okay, and that object I defined again, still mostly relying on tree-level intuition. Basically, as a product, the expression I just erased. So the z of rho is exponential, and then all the sources is this.
Yes, then is that definition is defined in oral perturbation theory?
Well, good. So ultimately, no. Okay, we will have object basically the same expression with modular subtlety that works. But again, that was not a top-down sort of construction. Here, I just started out with a tree-level picture. Can I just define some of the diagrams somehow? Let me just give a name of a G tilde. And then, now if I introduce the source term, there's a one extra Feynman vertex, which we talked about last time. So this is the source, okay? And then momentum coming out, okay? So given the fact that I have a one extra Feynman vertex, and then I had this big gigantic G tilde object, right? Which is defined as a sum over diagram. Okay? And then we can start drawing diagrams like that. Then I can sum over that object. That's how I define the generating function z over rho. You see, this is very bottom up, and then somehow, defined somewhat ad hoc level. Now I just want to give you a top-down rigorous definition, okay, without relying on perturbation theory picture. But obviously the blob we will still try to interpret as a perturbation series. Okay? So that's where we're going. Okay? Good. So to this end, we will do the following. So to this end, we will do the following. So take our Hamiltonian density, which could include, which might be possible to split into these two. Okay? But in the first path, I don't care whether there's a nice splitting or there's a notion of recoupling or not. Okay? But you can just think of it as having some Hamiltonian. All right. Now, as we did already, I'm going to modify that by having an additional term. Like this. So we are going to analyze this in two different steps. Okay? So we're going to analyze this to different steps. So we will use Dyson's formula, which I will remind you momentarily. But let me just do it right away. So we will do it Dyson's formula, but we will analyze this construction in two different ways and then compare each other. So let me first remind you what was Dyson's formula. So we started out the discussion starting from an interaction picture. So what was interaction picture? So first of all, there was a Heisenberg picture. I'm not going to review everything obviously, but here is a super quick reminder. So here, if I had an operator in the Heisenberg picture, I'm suppressing spatial index, okay? This gets rotated fully by entire Hamiltonian. That's the Heisenberg picture. Interaction picture, the operators rotate only according to, if you like, this is a free part or whatever the part that you understand well. Okay? And so that's the difference. Then you probably remember that is that in the interaction picture, so operator evolve according to, say, free part, but again, this is the quant, the part that you understand well. And then the state evolve according to, so if I have a state in interaction picture, still revolve according to the rest. So that rest can be written as, so basically it evolves according to full Hamiltonian, but you have to subtracting what? This part. Okay? So from this, we were able to derive an equation, evolution equation for state that evolve according to the Hamiltonian, which I'm about to write down, which is nothing but the interacting part of the Hamiltonian, but evolved by 3 parts. Okay, so that was sort of the summary. And then we solved this equation because by construction, we set it up the picture such that we understand everything about this part of the evolution. So the remaining question was, can we solve this equation, right? This evolution equation. And then that solution we call interaction picture time evolution operator, right? And that was given by time ordering of this. So this is a quick summary of interaction picture. Okay? And this was the Dyson's formula. Now, what I'm going to do is the following. Imagine you had some quantum field theory. Okay? And then there's a part that you understand well, there's a part that you want to actually understand better. Okay? But nevertheless, we're going to split it into this form. So we're going to run this Dyson's formula analysis. Okay? But we are not going to use, for instance, Week's theorem and Week's expansion. So we are not going to do this because this is intrinsically relying on perturbation theory. Remember, Week's theorem relates the time ordering of an operator in terms of creation and annihilation operator. And the notion of a creation and annihilation operator is intrinsically based upon a perturbation theory. So we are not going to do that for now, but we are going to only rely on that formula, which is just true in general. So we will do 2 different ways. So version 1 of analysis, we will do this way. So there is a H Hamiltonian density of the original QLT that you want to understand, and then rho dot phi, the source term. So we will run this Dyson's analysis by taking the full Hamiltonian as my, if you like, base part of the Hamiltonian. Remember, here, Dyson's analysis take this part to be base, this part to be interaction or perturbation. So, on the other hand, in the version 1 of our analysis, we're going to take the entire Hamiltonian as our base Hamiltonian. So I put the hat to remind you that this is one version of analysis I'm doing. And then we are going to take the source part as our perturbation part. Okay? So that's the first analysis I want to do. So in this case, in this way, we will get a expression for Green's function, which is non-perturbative in coupling constant hidden inside of this H. Okay? And then in the second version, we're going to do more conventional analysis. So now here, I'm going to really take this part to be my base. So let me just put base, just to distinguish. So this part I will take as my basis for the Dyson's formula analysis. And then this whole combination I will take to be my actual interaction point. And then I will compare these 2 versions of analysis. Okay? As you will see, this is useful to do. Let's do it. Is it clear what I'm gonna do? Yes.
H prime in this case is what?
H prime. You mean this H prime?
That H prime.
The same H prime. So this, for instance, this can be a free Hamiltonian. Okay, free propagation of a scalar. This can be an interaction of a phi to psi bar psi, that kind of thing.
So we don't take the interaction to be rho phi.
In the first part of analysis. Yes, no, we're not gonna include it. So H prime is included in this part. This is a full Hamiltonian.
Okay.
Okay?
So I'm just confused. H. Why is it the H not at the bottom?
What is this?
HB, it makes sense, but why did we write H0?
Sorry, what?
Yes, here.
Why don't I write B here?
Yes, because you wrote H0 and then
I could have done that. I feel
here.
like this is naming. So the point is which part I'm taking as a basis for the Dyson's analysis, meaning the part that we assume to understand fully. Which part we are taking a sort of perturbation part, as a perturbation part. Okay? And then we will do the analysis. The same Hamiltonian, only the division is different. That's all. Good. So just looking ahead, the reason why this is interesting and useful is because this version allows us to do basically perturbation theory in powers of a row, but non-perturbative analysis in any order of a coupling constant hidden inside of H prime. Okay? So in that sense, this analysis will give us non-perturbative expression for Green's function. But the second version, I split this way, so that now I'm going to do perturbation theory not only in the row, but also actually a coupling constant I'm interested in. So in this picture, I will get a Feynman diagram interpretation. Because I have a free, I'm treating this as a perturbation, so I can start talking about the Feynman diagram expansion. Hence, once I match these two versions, which I will establish, then we have an interpretation of a full general expression, valid in all orders of perturbation theory, but in terms of Feynman diagram expressions. Okay, so that's where we're going. Is that clear? Okay, let's then do it. So version 1. So in this part, everything I will just put hat to remind you I'm doing that analysis. So in that picture, did I erase it? So yes. So Dyson's formula, I'm just basically gonna do this. This is an interaction picture according to whatever division we are doing, right? So let's first remind you in this version, interaction picture field in this version is 1. Like here, the operators evolve according to base part of the Hamiltonian. So this is nothing but actually full Hamiltonian picture of the normal sense. Sorry, Heisenberg picture of the normal sense. Is that clear? Interaction picture operator evolve according to the base Hamiltonian. But here, base Hamiltonian is the full Hamiltonian, other than the row part. So here, the interaction picture in this first version of analysis is the same as a full Heisenberg picture operator. Okay, good. So, very good. So then we are ready to write down. So here we're gonna basically look at a vacuum to vacuum transition amplitude. So here, therefore, U, I, hat, again I'm putting hat to distinguish this operator, otherwise known as a S operator, is given by time ordering of exponential minus I before X. And I have to write down basically only the perturbation part in interaction picture of that scheme. So here, what I have to write down there is this is a classical configuration. So there's no sense of operator thing. This is just a function. And then I have to write a field in interaction picture of that thing, right? Which is nothing but Heisenberg picture. Are you with me? Okay. So let's now consider, and then I'm gonna use the following. So I'm gonna use this notation, big omega. This is a physical vacuum because I'm not relying on any perturbation theory in this slide. So this is a physical vacuum of fully interacting QFT. Okay, so this is the exact vacuum of a full Hamiltonian. Okay, and then we were using this thing for free vacuum. By free vacuum, I mean vacuum of free part of the Hamiltonian. Okay, so with that set up, now we want to look at the vacuum to vacuum transition amplitude. So we're going to look at this, right?
physical vacuum.
If you have a QCD, you can ask what is the vacuum of the QCD. If you have a Sungwoo-Hong theory, you can ask what is the vacuum of the Sungwoo-Hong theory.
What is the difference between the two? I think the particle must be based on the second one, the creation of particle acting on the second pre-vacuum.
Yeah, free field operator will act on here.
Yeah.
Yes.
Then what does it mean?
So you will see one sharp expression relating these two.
Yeah.
Momentarily. In the process of derivation, I will have to show how these are related. So you can wait until then and you can ask your question. Okay? Any other question? Yes.
Zero say is a vacuum of H0. Can I read H0 as HB or is it different from HB?
Yeah, okay. You mean this issue?
Yeah.
This is my sort of naming scheme, okay? So they have a fixed name, right? Free, perturbative interaction, sort of stuff. Let's say that. They have a fixed name. I just call like a base part versus perturbation part for the two different analysis schemes.
Okay, then zero says just really vacuum for H0.
H0, the free Hamiltonian. Which by construction means that there's no any excitation at all. Nothing is a vacuum. Okay, so let's look at this object. So what is it? So this is well, now here we go. So you can plug in time ordered. Oh, actually, this is correct. I need a space. I want to move this much. Do we have the experiment list? Yeah, that doesn't. So I want to define this as this divided by the vacuum. So basically, doing this is the same as saying that can I define my full physical vacuum, which is normalized to be 1, right? That's the same as this. But here, I'm just agnostic about the normalization. That's why I'm just putting this explicit. Is that clear, what I'm doing?
Can I confirm one thing?
Yeah.
I think the physical vacuum, so-called physical vacuum, is not defined at this point, right?
Well,
But you are using that.
Oh, okay. Let me define. So given H, right? So let me define. Okay, there are things that I need to worry about. So for now, let me define my physical vacuum as this, and let me assume that there's a unique. Unique this, meaning I'm not worrying about possibility of having many degenerate vacuum structure, which is ubiquitous by the way in field theory, but I'm not just running into that complication for now. Okay? So my physical vacuum is defined such that I'm doing the pure QFT, so I'm not worrying about the vacuum energy part. So I'm subtracting vacuum energy such that given a full Hamiltonian, vacuum corresponds to the zero energy state, and then I'm saying that I'm not worrying about the multiplicity of the vacuum. Okay? So I'm just assuming there's a unique vacuum.
Recalling the definition of the pre-vacuum, it was defined as
H0 acting on that is 0.
It was defined as the vanishing property of the annihilation operator.
That's right. And then if you recall,
it is much sharper definition than just
this is a general definition that relies on the creation annihilation operator, which exists for free field. So if you recall, then H in the free theory can be written as alpha dagger alpha in terms of annihilation. Again, if you act on that free vacuum, it goes to 0, right? It gives you 0. And then we had interpretation that vacuum, free vacuum, is the same as any excitation, particle excitation, because of that link.
Are you saying that Hamiltonian omega, the pre-vacuum vanishing condition is equivalent with the annihilation operator pre-vacuum vanishes?
It's yeah. I mean,
당연히 후자가 첫 번째 거를 의미하는 건 맞는데
네.
첫 번째 걸로 후자를 어떻게 보일 수가 있죠?
It's a free theory. You have an exact relationship, right? for free theory, other than the operator ordering issue, this is basically omega up to numerical factor, which I'm not worrying about. This. So if you define your vacuum as this, obviously this is 0. So if you accept this as your definition for the free Hamiltonian, this I guess should imply this, or vice versa.
그러면 알겠는데 일단 아까 그런 것 같아요.
Okay. Or this at least applies the fact that number operator is 0. The fact that no excitation means that that thing doesn't have any excitation at priority. Right? This is literally number operator for free theory. So free theory, nothing to hide. This is you have an explicit expression for everything.
네, 저렇게 다 가능한 이유는 넘버오프에서 일단 정의돼야 되고 그게 컨저브 컨디티가 되는데.
Well, we can always do that, right? Here.
아, 그러니까 인트랙션 또 저걸 비슷한 걸 정의하려고 해보면.
I thought your question is about the free vacuum.
아, 예.
Okay.
네. 그러니까 해밀토니안에다가 오메가를 치면 0이 된다는 걸로 저걸 정의할 수 있어요, 저렇게.
To the extent that you can understand the spectrum of given interaction QFT Hamiltonian. Right? And if that theory is well defined, meaning there is no instability and anything, you must be able to define the ground state of the field. Right? You may not be able to solve the ground state because of the limitation of the field theorist. But given a well-defined QFT, we must be able to define the ground state of the field theory. Modular vacuum energy issue, which I'm not worrying about because I'm dealing pure QFT, not a GR, quantum gravity. I must be able to define the ground state of whatever field, well-defined field theory. And this is my definition of that.
그럼 그런 엑스트라 레벨에서 정의를 하고
Extra level.
그냥 추상적인 그
Yes.
의미에서 저거 존재한다는 알기를 하고 표기를 하는 거고요. 여기서 그 어널리즘 오퍼레이터에게 배치되는 것은 정확하게 프리필드 티어리를 찾고 나니까 가능한 논이었고.
Yes, so you can define, so I would say this is the definition of a vacuum. And then it turns out that you can have this definition also in free field theory because you have an explicit relationship. Okay, so this is always a definition of ground state for me in QFT when I don't need to worry about the vacuum energy subtlety. Okay, so okay, with that, again, I'm doing the first version of analysis. And then let me remind you this, okay? Interaction picture operator in that analysis is nothing but full Heisenberg picture. This is time evolution operator. And then I'm assuming there exists a physical vacuum, which is defined by this. And then I'm assuming it's unique, okay? So then I want to look at this object. So this is a vacuum to vacuum transition amplitude with a normalized vacuum, so I'm just writing this way. If you like, you can just assume this to be 1 already and don't worry about that. But here I'm pretending to be general, although there's nothing to be general. So let me define this object as my zeta. Okay, so now you erase any memory about the free tree level analysis I just showed you. Okay, this is my definition of zeta. Good, so now you see that you can literally plug in and you do the Taylor expansion in powers of the row. So let me do that. So if you do that, you get the following answer. So let me expand that. Minus in over n factorial. And then I will get a row. Oh, I have to integrate. D for x1, D for xn. Then you will get this object. And I'm using the same notation, but now this is a fully defined non-perturbatively, and that expression is the expectation value with respect to the full physical vacuum, time ordered, and Heisenberg picture operators. divided by the normal of the diagonal. Okay? And again, in this definition, you should be able to write this in terms of a functional derivative of z with respect to rho's, right? This is literally coefficient of the Taylor extension, functional Taylor extension. Okay? So now we are in the moment to talk about this output, which is physical vacuum expectation value of time-ordered string of Heisenberg picture operators. Now, let me remind you one thing. In this analysis, I didn't need to even assume that this is either elementary field, right? This may be some composite crazy operator of that field theory that I don't care the details of it. So this need not be even a elementary field appearing in the construction of Hamiltonian. I'm just saying there's some operator that theory can give you, and then if I just take that out and then I'm just writing this down, I can still do this analysis. Is that clear what I'm saying? Because whenever I write a phi, you're so ingrained by the fact that that was one of the free fields. Forget that. Erase that. So this can be arbitrary operator, well-defined operator of the degree. Therefore, as we will talk about in detail, maybe today or next week, this operator in general is capable of not only producing single particle state, it can produce 2 particle, 3 particle, and particle some bound state, all the crazy stuff. Okay? So this expression you should take really as a completely general expression of QFT. Okay? Now, so that's the first version of analysis. Let's move on to the second version of analysis. So now I'm taking I'm assuming there's notion of perturbation here. Okay? Now I'm assuming the fact that I can split my Hamiltonian into say free part, if you like, and small interaction part. And then I just include an extra thing. And in this picture, still I can take this to be more general, but just to make a contact with it, now I'm taking I'm assuming that this is one of the field operator appearing in the free field. Okay? So the matching that I'm about to show works sharply if I now take this to be also one of the potentially field operator, or any operator that has a non-trivial overlap with a field operator that creates a one particle state. Okay? So that's what we are going. And you will see how things how matching can be done. Okay? So let me continue with the second version of analysis. So in version 2, then so interaction picture operator is an interaction picture operator now, genuinely, in the normal sense. And then I can also write down this object, which is time order, exponential. And then now I have interaction picture, interaction Hamiltonian, and then rho phi I. Okay? So now I really mean interaction picture operator here. Okay? Where that was Heisenberg picture operator. Okay. So now what I want to study is I'm going to define my generating functional with f, where f denotes a Feynman. Feynman in a sense now I will have interpretation in terms of Feynman diagram expansion solver. Okay? So I will define this as follows. So I will think about some regularization. So I take future time, go to obviously plus infinity, and then for past time, go to minus infinity, but I'm just going to use a regularized notation for a second. So now I'm going to write a tree vacuum. Okay, and I'm going to write down this. Here, t plus t minus, that's what I mean, because I'm sending this to infinity and minus infinity. And then, yes. And then I'm going to write this picture plus minus, but with the source turned off. I will explain the meaning of this and why this is a good thing to do. Okay? So let me first write explicitly this expression. T plus minus infinity. So now I'm going to actually write this down. So there will be sum over, well, I could have moved some earlier, and goes to infinity. This. So now what I'm doing is I'm actually expanding this. Okay. So I will have p4x1 So I'm going to expand in powers of rho still. And what you have is time ordering of gigantic expression e to the minus I. So since I expand this over, I just have this. And then I will have sum of phi. Over this object. That object is these two, right? Okay. Now, does this make sense? Well, a lot of things you have to understand, but at least the start is the starting point, sensible to you. Well, here I looked at the vacuum to vacuum transition amplitude, right? In that division, in that splitting. I'm also looking at the vacuum to vacuum transition, the second splitting version, right? So that's what I'm doing here. And then here, all I did was I just again did expansion in powers of rho. That's all I did. The only thing that I probably need to explain to you is this part. So what is the meaning of the denominator? Before I sort of doing the analysis of this part, what is the meaning of that? This is a vacuum to vacuum transition, but without a source term. That's what he said, right? So diagrammatically, let's ask, what are the possible diagrams? So here's the time, here's the future, here's the past, there's a vacuum here, then there's a vacuum here, then there's a time. And in the absence of a source term, what are the possible diagrams that contribute to the vacuum transition? You cannot have external lines, right? So in the presence of the source, you could have produced something out of the vacuum just using the source. But now you don't have any source. So the only thing that you can possibly have is sort of pure, what is known as a vacuum bulb diagrams. Something like this. That kind of thing. Is that clear? Therefore, in the absence of the source, this denominator is, as you see by I explicitly, this is the sum over all what is known as a vacuum bubbles. So therefore, what I'm doing here is that in this part of analysis, I'm basically looking at the vacuum to vacuum transition in the presence of the source, and then I'm factoring out all possible vacuum bubbles. In other words, suppose you had a diagram here, okay? Suppose you had a diagram something like, suppose you had a diagram something like this. But then, obviously, it is possible because now you have a source in the denominator. But you could think naively that, oh, okay, this diagram, but what about this times? Is a part of the same diagram? What about like that diagram, right? So naive expansion of the numerator could include this thing, for sure. But this denominator basically is saying that you just factor out all possible vacuum bubbles. Don't worry about that. And only look at the, if you wish, connected diagrams, which meaningfully contributed to whatever physical process you might be interested in. That's what this division, divided by this denominator factor means. Is that clear? Because I'm gonna pick any diagram times entire vacuum bubble. But denominator will basically say, forget about that. Just factor it out. Good. Now, that's the first interpretation. Second, for a reason that I will just now do, turns out that there's one-to-one correspondence between these two once you actually factor out the vacuum bubbles. So that's another reason why we are looking at this. Okay? So now what I'm going to do is that I will take this expression and show that this definition of formal definition of the generating functional is identical to this Feynman generating functional, which you have now Feynman diagram interpretation. Okay, you see there's this some number of interaction picture operators which you can use to create initial and the final state. And then you, in the presence of the interaction, as we have done, you can now think about the Week expansion. You have a diagram like this. So this has a Feynman diagram interpretation that we didn't, but I'm going to show that there's a sharp correspondence between these two. Okay. So that's what we're going to do. So let's do it. So plan is this with the coefficient of Green's function in terms of Heisenberg picture is identical to this. So to do that, let's do the following. So here I have this gigantic string of the time-ordered product of operators. So here, without loss of generality, let me take the time ordering. Okay. Okay. I'm just going to assuming particular time ordering now. Okay. Then that expression. So let me look at the numerator part. Numerator, I can write it as this. Let's forget about the time limit for a second, because in the end, t sub plus goes to plus infinity, so you can take this to be latest time in this expression. Although I did not write explicitly, this thing has this. And then since t sub minus goes to minus infinity, you can always take this to be the earliest time. Okay? With that, this expression can be written as, for now, let me just skip the time ordering. Basically, e to the minus t1 to t plus, yeah, and then you have this, yes, 1, t1, let me just skip the time thing, and then you have a t2 to t1, and then you have t2, keep going, and then you eventually have a tn, or I, and then you have a leftover time, which you have to run from t minus to tn, and then back in, right? So this is the form of that expression. I just split into things in a time order sense by governing time ordering. And note that this is nothing but ui t1 to t plus, and then this is ui of t2 to t1, and so on and so forth. So the whole expression can be simplified. Now let me withdraw the time ordering as ui t plus t1, and then I have to have this, and then I have to run t1 to t2, and then I have insertion of the second operator, keep going on, and then you have ui of t n minus 1 n, and then you have tn. And finally, you finish up with the last time evolution from t minus to t s. Okay, so that's the expression. Does that make sense? Now, recall that any of this subject satisfies the group multiplication law. So if this can be written as a product of the two elements, such as ui of t1 to some intermediate time. Let me call that intermediate time to be 0. 0, t2. You can already split this evolution from one time to the other as a one time to 0 and 0 to another time. Okay? So then, whole expression collapses into ui t plus 0, and then you have a sandwich. So let me just write sandwich form. Something like ui 0 t1 I t1 t1 to 0, and then you have a chain of all this same expression all the way through. Let me write this angle bracket of nth kind, so that you have a first, second, third, last, and then the last ui this leftover is 0, t minus 1 vacuum. Okay? So cut out sandwich, cut out sandwich, cut out sandwich, cut out sandwich, sandwich, and then you just left over this and that. Okay? So now you should be able to convince yourself. So now I have to deal with this, all these square brackets, and then you can convince yourself just using the definition, this is nothing but Heisenberg picture operator at T1, and so on and so forth. Some of you might be extremely unhappy if I move on. Should I move on? No problem, I have time. So let me quickly show that. So remember, Heisenberg picture operator at T is starting from the Schrödinger picture at 0, we have to evolve fully in terms of a full Hamiltonian. Here I'm assuming time independent Hamiltonian. Right? And then interaction picture compared to the Schrödinger picture is only running according to A to 0 part. Like so. Okay? So you can just put it back here. So Heisenberg picture T is equal to I T. And then you have to do the other way around. This. Yes? So remember, this is literally the definition of UI from 0 to T. Why? You do the full running and then compensate by the running by H naught. This is conjugate of that. This is P0 conjugate. But we also know that this satisfies basically the other way around. Hence confirming that expression. Okay? So what have we achieved? Well, starting from Feynman picture generating functional, I just did the numerator part. Okay, so numerator, therefore, is basically some mysterious factor times time order of n Heisenberg picture operators. I haven't done this yet, but we will. Okay, good. So let's continue. So I want to also take care of the denominator part. Okay, so this is good to go. So what about the denominator? That's also easy to deal with. So that's numerator. Denominator is basically 0, and this is what? This denominator is basically ui from t minus to t plus. Because there's time order. Right? Again, this can be written as ui of t plus 0, ui of 0 t minus. So that's the denominator. You see that denominator also has this factor, which numerator also has, other than time ordering of Heisenberg picture operators. Okay, those are common factors. Okay, so what is it? So what is this object? That's what we need to understand. So to understand this object, let's take either this or that, doesn't matter. So let's just consider one of them. The other is identical. So let's just consider t minus 1. So as t minus goes to minus infinity, I want to know what this is. Okay? ui 0 t minus that. I want to know this. Well, first of all, this can be simplified already immediately. So what's the definition of that? Well, remember this is conjugate of t minus 0 conjugate, right, according to this part of this question I just did. So that means that is evolution by the full Hamiltonian compensated by H naught and evolution dagger. So the vacuum. And then this is, again, conjugate IH E minus H0 E minus vacuum, right? Free vacuum. And the definition of free vacuum is such a way that if you activate by the H0, they give you basically the vacuum itself, or the eigenvalue is 0. So that object collapses into asking, in the limit t minus goes to minus infinity, what is this quantity? That's the question. All right? So let's just do it. And this question will provide some answer to the relation between full vacuum and then free vacuum. Let's actually look at it. So let me give this. So let's assume we have a full Hamiltonian, right? So as we talked about given full Hamiltonian, we talked about unique ground state, which we already did. But also, let's imagine some non-trivial state, which say we have energy, En. And we sort of imagine the picture, there's a ground state, okay, which is 0, and then either discrete or continuum with some gap. Okay? That's what we were thinking. Now then, this can be expressed as follows. So given this, I basically need to look at T minus acting on the free vacuum. But let me insert a complete set of state. So that, let me write it as some complete set. Let me just write this symbol. It can be discrete, it can be continuum. I'm just going to insert the complete set. So this can be split into two pieces. So first, there's a vacuum. So if it is a vacuum, I get this of the full Hamiltonian. And then, same limit. And then we will have a n, which is not equal to vacuum. So this corresponds to all meaningful excitation of the theory. Okay? And then I have e to the I, E, n, t minus, n 3. So that's the answer for now. Okay, so that gives me one picture. So somehow this side, if I do the infinite time evolution, at least it has a contribution which is proportional to the true vacuum with overlap between the free and the true vacuum. Okay, so that's that piece. That piece does include this contribution. Now, what about that? Any overlap between the free vacuum to non-trivial excited state of the full Hamiltonian? Okay. Now, I will answer this two ways. One word, two equations. Let me just answer the first version, just word. Now, so by definition, En for any non-trivial state has a non-zero energy. Okay? If you're thinking, what about the gapless mode? What about the Boson mode? What about the gauge boson? What about the Carl fermion? But if you want to talk about non-meaningful entity of that thing, you will have some non-zero energy moving. Otherwise, you declare that to be non-existence. Okay? So any meaningful object or state has a positive energy. Then, if I take the infinite time limit, you get wild oscillation for each chosen n. Okay? For any fixed n, there's a wild oscillation phase. You expect that there is a cancellation effect. Mathematically, precisely, not that I have done that exercise, there is this theorem in Fourier analysis called the Riemann-Lubeck lemma, that if you have a wild oscillation induced by this wiped out in zero. Okay? That's a word version of analysis. Hence, we expect that that is true state by state, therefore this entire contribution will collapse if I take this infinite time limit. Okay? Now, if you don't like that word, let me write down a word equation. So here, I'm gonna do the following. So instead, t minus goes to minus infinity. Let me tilt a little bit towards the complex plane, just a little bit, okay? So then, again, there's this state by state, which is not equal to vacuum. So then you will have En, and then here, T minus, let me just write it down explicitly. What do you have? What do you have? Minus infinity with small immediate component turned on, and what do you have? N 0. So this thing does include, I guess if I put the sign correctly, epsilon T n infinity. So I'm going to keep that to be positive or small. But only in the end, I'll send this to 0 from a positive side part. Okay, so if you take the limit, all those contributions will die off because of this. And then you can take that to be 0 in the end. If you worry about what about, does this two limit commute? Okay. Open the math book, look at the Riemann, the back lemma, go and help yourself. Okay? So this sort of trick is known as, if you wish, I don't know if it's official, vacuum saturation. Sometimes some people put the trick. Okay? So by taking a large time limit, basically you project at every state except the vacuum. Okay, so that's it. All right, so coming back to original business, what have we achieved? So there's a numerator, there's a denominator. So let me write down what we managed to collect. So therefore this first, send, you only pick up a true vacuum contribution except this wave function. The other way around, so you pick up true vacuum thing, except wave function. And denominator, the same. So this is 0, vacuum, 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 how many vacuum? Vacuum. Okay? Hence, you can look at it. Where's my original? Here. So now we can get rid of this. So now you can collect everything. So the Feynman object here. So if I define everything this with the limit as my Feynman Green's function, you see that the Green's function in Feynman object in the limit where t plus minus goes to infinity properly, then you see that that cancels out, you get this time ordering of Heisenberg picture. Again, I'm just writing time, but I mean this flex. And that was the object we defined non-perturbatively. Okay? Hence, what have we learned? If you have any field theory, whether it is a perturbatively defined or it doesn't accept any perturbation theory picture, you can always define your generating function by shifting to total Hamiltonian with the work times phi. Well, you might say, where's the Hamiltonian then? If you don't have a weakly coupled picture. So if you don't like that, let me just stay in the perturbation theory. Then you can shift it, and then you can define